has nothing to do with this class. Is the following. You see, there are very interesting things which are called spheres. Just so you know, so sphere. Just to make sure we're in the same page. This may be explicitly realized, if you want, as the set of x in Rn plus 1, such that norm x, so the usual norm, is 1. This is a realization of a sphere. Well, okay, but some of these gentlemen are just learning about manifolds, and so this is, in some sense, where's manifold? And these have differentiable structure. So these are coordinate charts. I'm going to talk about coordinates today, so I'm happy I mentioned this. So coordinate charts which is to say open sets in the sphere, and coordinates on these open sets. So a coordinate x, which maps the coordinate, say back to the sphere, into isomorphically onto open set M. So I'm repeating what Professor Bertrand was perhaps discussing in manifold coordinates. Who hasn't heard a sphere, if you wish, this is the true sphere, and maybe here is a special open set that you can, where you have coordinates, and this coordinate x maps it someplace into Rn. Well, in this case, if this is the two sphere, this would map this into R2, and maybe map this coordinate thing onto some open set here, V and R2, where you have coordinates. Right? So in this case, x requires two functions. And these coordinates on the sphere, so every we have several German, you're also German. So we have at least two German people here. They know what the shell atlas is. At least in the old days, we all had something called shell atlas. You don't know it anymore, do you? Okay, it's a big, every German in my age and slightly older, slightly younger, knows the notion of shell atlas. It is a book which was published by the Shell Oil Company, which is, on every page is a map. And it's a huge book, it's very good, high quality map. Everybody has it in his car. And I asked we have an old car, and I don't have a GPS on this car, so I asked my wife to look up in the Shell Atlas what's going on. But it's also interesting in the Shell Atlas you have the license, in Germany the license plates, for example, HB means Bremen, OS means Osnabrück, MS means Münster. And sometimes they're obscure license plates, and you want to know what it means. So some crazy guy is driving you off the road and you say, where is this guy from? And so you can figure out where he's from his license plate, and it's in the Shell Atlas. So you see, this is maybe contained in the Shell Atlas. Right, on page 800, on page 342 perhaps. So you're looking, this is maybe a page. Okay, and so these things are compatible. If you have overlap, they're compatible. What that means is that if something is said to be differentiable on this U and also on U hat in the same way, then it makes the same sense on the overlap. So that means it has a differentiable structure. I mean, change of coordinates is differentiable. It is the fundamental notion in modern mathematics, even in algebraic structures. So what is really a manifold? It means that you have coordinates and they're local, but they're compatible. The notion of differentiability in one coordinate system, maybe here's U hat and you have a coordinate here X hat, and you say something is differentiable if it's differentiable in X. It's the same thing as saying it's differentiable in X hat as long as you're in this intersection. Keep this in mind, particularly those of you younger people who are taking Professor Pittel's course. This is the notion of a differentiable manifold. So this is a very old notion, but took a long time to really be understood in mathematics. It's extremely important. Okay, when you have, I'm just repeating for those who just walked in, I'm repeating something that Prabhat and I were talking about. We weren't sure about something, right? And this something is related to spheres, and these spheres are differentiable manifolds in a sense. And when you have such a thing, you have something called diff M. Okay. Now these are the diffeom set of, it's a group, and these are the diffeomorphisms of M. And that means the globally defined mappings. Here, these are just local coordinate charts and so on. These mean the global mapping. So this means it's a self-map from M to M that has a differentiable inverse. So it's a differentiable map, which is injective, surjective, and so on, and it has a differentiable inverse. Diffeomorphism. You heard the word homeomorphism. It means on a topological space, it preserves the topology. This means it preserves the differentiable structure. Yes? These, you should think of these things as, again, it's motivation for my lecture today, these you should think of as global coordinate change. Global change. Okay? And there is one very nice, this group. Now, you don't know anything about mathematics. You know a little bit about mathematics, but you're just starting out. Yeah. And so you're looking at this, and you're just starting out, and you should say, well, he told us about this stuff, and this appears obviously in other courses and so on, but this thing is a group. I ought to understand this group. Yeah? And it's pretty obvious. If you're going to do anything at all in this subject, you should understand this group. Yeah? So you should say a goal, some understanding of this group. And then you should say, I am stupid, because this group is probably really ridiculously big. Okay? Why? And I can't possibly understand this group, at least at first. How big is this group? Well, if you take a rotate, everybody knows the from high school rotation of the sphere. So you choose some axis of rotation, and then you rotate around this. Choose another axis of rotation, you rotate around that. Those are diffeomorphisms. Clearly, they're perfect. And then you start composing these rotations, and you generate a group, and that group is a very nice group which we understand. That's a finite group, a finite dimensional group. It's not finite because you have all these various rotations, all these axes. It's a finite dimensional group. That's called the orthogonal group because it's somehow preserving orthogonal structure. But that's some group of matrices, and that's not so bad. That's not so bad. But if you take one of these things, rotation, and move it a bit, you understand what I'm saying? Take a rotation, but just deform it a bit. Let me give you an example of what deforming a bit means. You should say, this professor always starts too high. He's talking about the two-sphere. Let's talk about the, well, he gave very nice stupid questions. I like your stupid questions. Yes, good. And we should start with a zero sphere. Well, okay. That's not good enough. So, but maybe the one sphere is good, right? And everybody in high school writes this number here, although we really are unsure what it means. And here's 2 pi here. And if we have a map from the one sphere, which was from 0 to 2 pi, with 2 pi identified with 0, you can think of it as this thing. That's the same thing as a function map. Say it maps 0 to 0, and it has to map 2 pi to 2 pi because it has to glue right? So you can write the graph of a diffeomorphism of the one sphere as a monotone function, right? It has to be bijective, it has to be smooth, it has to be differentiably invertible. You all learned that from me in first year course. It's the inverse mapping theorem. So just take a monotone function like that. That's the diffeomorphism. So the space of so diff of S1 somehow is related to monotone functions. Yeah. And that's very, very big. So this guy is talking about a very big group, right? You can imagine what's this, infinite dimensional. We talk about bases of things. I mean, well, it's not a vector space, it's a group, but somehow. And it's just very, very big. Okay? But then from this thing, you say, if I take a monotone function, and there's another monotone function that I like, maybe, this one, and I hope, deform it back to that one, right? So if I'm lucky, if I have a monotone function, which is an element of this group, I can deform it back in a smooth way to a linear function. This would be a dream. Now, that linear function I just wrote there is the identity, right? It's the identity. But that's because I started at 0. I could have made it different, right? So these would be the linear mappings thing. And I hope that these linear things correspond to rotation. The mapping, this one's just the identity, and then if I start, if here's the point 1, if I make 1 go to pi over 2, then maybe 0 goes here, and so on. So not so bad. So then you have an idea, and you should introduce some intuitive idea coming from your feelings that diff S1 is retractable to the group of rotations. All right, by some sort of retraction. Now the trouble is, you have rotation this way, and you have rotation that way, and they're somehow not retractable. It's a bad thing. So let's look at plus here. Let's talk about those rotations which preserve orientation. Okay? So that's what you should do. This is all the first thing you should do in Professor Petrov's course. Say, what's the first manifold you know about? I would say S2, and then if he's a good professor, he will tell you, no, it's far too complicated, consider S1. Or consider S0, but that's too simple. Then S1. And then this group is horrible because it's just really big. So it's infinite dimensional. So, but you can retract it to a finite dimensional set. And so, after some thought, you say, what about the orientation preserving diffeomorphisms of the two-sphere? Just start low dimensions. We need to understand this. So he needs to understand this for something he's starting to work on his thesis. Right? You want to understand this thing. And it's the same thing. You have a diffeomorphism you love, the identity, as far as I'm concerned. Take the identity and you just move it a little bit, it's still a diffeomorphism. Right? So this is huge, but maybe retractable. We haven't even defined what that means. Say, just like the one sphere, to a group of linear transformations. And that's what I was talking about. If you're very lucky, this thing, linear transformations, say, generated by the rotation. The rotation. Now here, you have rotations on many axes. So it's a very big group. So you have rotation on that axis, you have rotation on this axis, and so on. You have all these rotations. This is a finite dimensional group. If you think of it carefully, you will see that you have a choice of the axis, and then the rotation. So, and the arbitrary rotation. So the choice of the axis is 2 dimensions, and how big the rotation is another dimension. So this is a 3-dimensional group. 3-dimensional group. It has a name, and this group has been studied a lot. Okay. And it appears in physics, in spin structures, and I will lecture on spin structures in the next physics seminar. So this is very closely related to what is called one of the first quantum mechanical things, understanding the hydrogen atom, which amounts to understanding something like spin. So it's like that. You have this wonderful finite dimensional thing. So here's the linear group. And then you have this horrible big thing, which is infinite dimensional, which is the full diffeomorphism group of preserving the orientation. And it's retractable. That means there's a wonderful flow that retracts this whole thing onto that. There's a flow, that whatever a flow means. that doesn't change anything at all, it retracts that onto that. Okay. If you're worried about it is, ask the professor, what the hell is it? And the professor, if he's a good guy, will say, well, suppose you have the circle. Yes, the circle is very much, here's the circle, right? But take out the origin, right? And as you see, there is a flow of the outside onto the circle. Well, you see it, right? You flow the inside of the circle and flow the outside of the circle. I can even define it, I think. Right? Let me see here. V is a vector here. And every flow you should write time times, well, I'm going to start out at time 0. So 1 minus time 0 times V plus time times V divided by norm V. Always think of flows like this if you can. Time. So you see what happens at time. Time equals 0. Nothing happens. Right? Nothing happens. Here's V, and nothing happens. And at time equals nothing happens. So this flow T of V, so flow 0 of V equals V. And at time equal 1, flow 1 of V, this part goes away, V over norm V. Right? So I crunch it down on, you ask your sister who's 6 years old to do this, and she'll do it. Maybe it's a baby, it's even better. The baby's grab it and crunch it together. Right? Okay. So it says that what is going on here is really the key thing that's going on here. If you look at this two-dimensional space minus the origin, what is really going on here is the circle. Right? We say in big boy language, we have only boys here today. We say in big boy language, this complement is homotopy equivalent to the circle itself. So the word here that you see in mathematics is homotopy. And the other word you see in here is retraction. They're not equivalent, but they're effectively equivalent because, yeah. Okay. And fortunately, I studied yesterday, asked me a question yesterday about diff S2. You see, I forget everything from my things in the past. It's a good thing because I have to it's because I'm old, but it's good because then I have to reprocess it and then I understand it better. So diff is homotopy equivalent to the linear group. In fact, this group has a name, so let me just name it. It's O3, and if you put plus here, that means it preserves the orientation. It's called SO3. It doesn't matter what it's called. It's just what it is. And you can write it down with matrices. So that's what we need for Prabhat's first considerations, right? He's happy about this. It has a consequence. It's a standard known result. I thought it wasn't bad. I couldn't prove it yesterday when he asked me. I just was too tired. So I can prove it now. But then you start thinking, I was a little optimistic when we were talking yesterday, maybe this is true in general. Maybe there's something true in general. Yeah? And so you say, what about higher dimensional spheres? let's maybe higher dimensional manifolds, I don't know, but let's at least talk about spheres. Well, to give you an idea about mathematics, I think this question has not yet been answered. So the situation is at least it is known. And now I want to tell you something about doing mathematics. You should take serious people seriously. Okay? So, and you should I talk to a lot of people all the time. Where are you going to go? I talk probably about where he wants to go to graduate school. I don't know, Deepak, where you guys are. We talked about graduate schools a little bit. You want to go where there are serious people that should be taken seriously. You sit around here at Jacobs University and think, I want to go to some cool place which is famous. That's totally irrelevant. You want to go to some cool place where there are really serious people to be taken seriously. And you've got to meet these serious people. We talked about with Nico with that also. You've got to make sure you know who these serious people are and where they are. Yeah. Well, and I will mention two serious people here who I read yesterday. And I knew they had results on this subject. These are two people, John Milner and Sergei Novikov. Fortunately, they're senior statesmen. I'm also senior, but they're senior statesmen in this area, topology, differentiable topology. And very bad examples. For I think already n equals 7 and 8. So bad things start happening in dimension 7. There's some reason for that. Some physicists will probably know about dimension 7. Bad things start happening in dimension 7. That was what we talked about yesterday. Here's an answer. And you see, everybody here understood what I just said, so there's nothing, right? And it shows you can come close to interesting mathematical research just by talking and thinking and so on. You might think that trying to understand these things in some generality is too much. But there have been recent developments that might help. Okay, that's my little blah blah for the day. Not propaganda for the day. Now, the reason I did this is I pointed out that you want to understand things by their coordinates. And so this is my lecture today is based on your question, Nico's question last time. He could not believe that this whole thing really truly depends on a coordinate in what we talked about last time in the formal power series. And the reason he couldn't believe that is we hadn't really talked about what is a coordinate. Right? So I think one of the very interesting things to formalize, maybe not dwell on it, but formalize what is a coordinate. Right? So let's start here. So what is a coordinate? And I will speak here of local coordinates at 0 in complex analysis. course, is complex analysis in one variable. So, in complex analysis in one variable. And I purposely put in here this word because I'm willing to bet you've never thought about what is a variable. And what is a variable and what is a coordinate are closely related concepts. Okay. What is a variable? It's not so clear what a variable is. It's not so clear what is a coordinate in these things. Well, I say that Kevon is right. He's my good friend who understands much more number theory than I understand. And he says, first of all, if you're going to do any of this stuff, I know what he's going to talk about in the next lectures. He's talking about geometry over in characteristic P, and so finite fields. So yeah, I'm talking about geometry over the complex numbers. So what Kevon's talking about here maybe is this over this field, right? And maybe he's even talking about it, or even over this field, right? Maybe. Look. And those are the finite fields. And here you do number theory. And therefore, you do operations that I call are finitary, and they're very good for computer science, or recursive at least. Your operations must be defined somehow without the notion of convergence, right? You want to define some operation on a computer, which is take the limit of something, is a very non-trivial thing, right? I mean, but you want finitary recursive operations, right? And so what you do is you look at some field, and then you look at the formal power series over that field, right? I know for a fact Kevon is interested in this. And one of the key things is in here is the stuff that, from my point of view, vanishes of order 1 and higher. So I write it like this. Order 1 and higher, maybe we write just x and then all possible multipliers of x. So a typical element in here is a formal power series that looks like that. Those are the key things. And that's what I want to look at here in complex analysis. And this thing has a name that you have to learn how to write in German. It's M. Always. Okay. Yeah. So it has very nice properties. No, it has wonderful properties. F is this thing, M is itself. Itself. Are there two S's in itself? Just one. It's like the German rule. They stopped making two S's to go together. Or two T's. You know, there was the famous one in German. No, okay, I have to get it right. Ballet, I think is correct. Theater. So ballet theater, it has three T's. But now in German, you're allowed to cancel it, right? I think. Oh, there you go. Yeah, and you have to look in the Duden, and I think you're allowed to cancel one of the T's. Yeah, ballet theater. Okay. So German has become, it was 3 times as complicated as other languages, and now it's 2 times as complicated. So this thing itself is an algebra. So it's a subalgebra, right? take linear combinations of things in there, that's okay, and you multiply two things and then you stay in this thing, it's okay. And plus, if you take anything in M, in this thing M, and Q, anything in this formal power series, right? Take Q, anything in that formal solid, then P times Q is again in M. That's a good property of that thing. It's stable under, you have to think of it this way. You hit it from outside and you still stay in it. Okay? You know stuff like that. For example, if you take the even numbers in the whole numbers, or the integers, and you multiply an even number by any number, it's still even. Right? So that's something like that. Okay? So, yeah.
So the notion of an algebra is just something that you take any two terms, multiply them, they're still in there, and you can add two terms.
That's right. But look what look very carefully. Take anything in it, and then take anything, no matter where it is, and multiply, and you stay in it.
Okay.
So you hit it. It's what I was just saying about it. If you look at the example of M equals something like the even number. In the integers, right? If you multiply anything in M, any even number, by anything, you're still even. Okay? Yeah?
But you need to multiply by some integer, at least.
So, oh yeah, but
you cannot multiply by
no, you're regarding this as a subalgebra of that.
Oh, okay. Yeah.
So, I'm sorry, yeah. So, this is sort of a fundamental subtype thing, okay? And these numbers, these things are very important, and you should study these things in various contexts. This is the notion of an ideal. And Dirichlet really invented this notion, and purposely, it's like you know, Archimedes took a bath and he floated and he understood what was he was understanding some physical thing.
Volume.
So something, yeah, I don't know. Some physical. You're a physicist. What did Archimedes understand?
I think it has the volume of water replaced is equal to the volume.
Yeah, something like this. Something about water replacement. I don't know. This physics is way too difficult, right? And then he ran through the streets saying something funny. What did he?
Eureka.
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 Eureka, which means I found it. Eureka. And Dirichlet ran through the streets saying, "It's ideal." No, he did. I mean, that's the reason he called it an ideal. Okay. So this is a fundamental thing, and here, this thing M above is the maximal ideal. In this power series. Now, I am not a number theorist. I know very little about number theory, and I'm doing these things over some finite field of something is very difficult for me. Okay, but this discussion has nothing to do with the field, right? It only has to do with the fact that the operations involved here are finitary. That means if you have two power series and you multiply them together, you have to add up some things when you're multiplying, but it's only finite combinations, right? It's combinations in algebra. So the operations are algebraically defined, and so everything here doesn't matter. So here in complex analysis, in yesterday's lecture, we talk about, and now I'm going to change the notation just slightly. C is the field, and I want you to talk about power series in big Z. It'll help me in my notation. You can imagine, because little z will be recorded, okay? So this is just the same thing that Caitlin's interested in number theory, but over the complex number. Okay. And remember yesterday, here, we have something that Kevin probably doesn't have. You have to ask him if you see him at lunch. Yeah.
Just have a quick question. So if we talk about this subalgebra, so x times the formal power series,
Yeah.
so this is basically formal power series which are non-invertible.
That's the way to look at it. We know that the units in this ring are the zero term of the power series development has to be non-zero.
Yeah, there it will be 0.
And right, so so in some so just keep asking your questions. This is the best way for me to lecture, answer questions. So as you see, more or less, this thing. Well, let me do the complex numbers. This thing, this formal power series ring, is in some sense this. Not only in some sense, as a vector space, it certainly is that, right? It's what you just said.
Yeah.
I split off the top coefficient, A0, and these are the, right? So, right? So, you can see, it's very amusing, that if you mod out by this, you mod out by that, you kill that, right? And that's the complex number. So that's the way to think of this, actually, right? Just you're modding out by this maximal ideal, and you get the complex numbers. Okay. When you learn algebra, remember I told you that. Okay. Algebra is there to be used, and this is one of the places to use it. Okay? Okay. Now, what would be the notion of good isomorphisms from the point of view of complex analysis? Complex analysis. From, let's write it this way. For some reason I write it from, I'm going to write it this way, if you don't mind. For some reason I have in my head a certain diagram and I want to write it that way. It's just my own craziness. Okay? So, isn't it true that if you have something, this is the stupidest thing in the world, that you should look at the good isomorphisms. What are the isomorphisms of this thing? Right? First of all, what are the isomorphisms of this thing? Somehow. Right? So it means algebra isomorphism and so on, so on, so on. Right? What are the good isomorphisms of this thing? Well, it's completely stupid what an isomorphism is determined by. It's determined by W equal P of Z, where P of Z is equal, the good, yeah? Well, what has to happen? You have this maximal ideal here, which is unique. You have this maximal ideal here, which is unique. It has to go to that. So W has to go to Z. No, it's not Z, but it has to go to something Z plus higher order terms. And maybe a constant here in front of Z. I don't want to make a constant. You agree? Right? It has to be. You have no choice. Right? So you have, and you, W has to be equal to P of Z. What that really means is that if you have any Q, which is in this power series ring of W, it gets mapped over here to the composition Q of P of Z. Right? You stick in, isn't that right? Do you want to go through that again? Yes. Okay. You have, where does W go? It has to go someplace over here, right? W generates the maximal ideal here, and Z generates the maximal ideal here. Well, it better go to a generator of the maximal ideal here. And if something here doesn't have a Z term, has only Z squared terms, if you look at all operations with Z squared terms, you're not going to get the whole thing. You're not going to get, so you have to have a Z here. Z plus higher order, right? Okay. So that means, okay, now that you know where W goes, you know where everything else goes, because everything else is a power series of W. So Q here goes into a power series development of P of Z. That's it. That's absolutely it. That's absolutely it. Every isomorphism that can be written is written in this form. Okay. Well, where the constants go. Okay. Okay. What does it mean, good? Well, that's first of all what an isomorphism is. But what does it mean, good? It means good, it preserves the notion of convergence from the point of view of complex analysis. I said from the point of view of complex analysis. Right? So you see, you have something here in W, something here in this. We have this notion of radius of convergence. Yeah? Yeah? Kavan doesn't have this notion of radius of convergence. Kavan's number theory, well, maybe he does. But I don't know enough about it to know what it is. So ask him if he has a notion of radius of convergence. Right? It's interesting. Maybe there's some good notion. Well, maybe you can write down the same thing, because it's just the radius of convergence is 1 over lim sup. Uh-oh! Uh-oh! Lim sup is, we better, if we're over some other few, I don't know what lim sup means, right? I know what everything else here means, I hope. Right? I know everything, you know, and yeah. It's not so clear. You need to be in a field where you have nth roots. I don't know, do you always have nth roots? I'm not so sure. And absolute value. And lim sup scares me really a lot if you're doing algebra. Right? But maybe lim sup in these finite fields just stabilizes someplace. I mean, it's only finite, so you don't even have to take a limit. It's probably easier. Okay. So that would be the radius of convergence. Okay. So you know that, and this is where we're coming to your question. Okay. So we know we have, and this thing depends on the coordinate. Right? This is what we've talked about. So let's formalize this and get it straight. Okay? So we have this, what I called last time, and I'm going to write it vertically, O, 0. These are just the germs of holomorphic functions. So let's remember, since I gave a bad lecture last time, what that means. A germ is an equivalence class, so a germ is an equivalence class. And what what do you have? You have a neighborhood U of the origin, and you have a holomorphic function on that neighborhood, and you have a neighborhood V of the origin, and you have another holomorphic function on that. And you want to define F is equivalent to G at 0. It means that there exists another neighborhood, I don't know how many, W, contained in U intersect V, such that the restriction from U to W of F equals the restriction. That's restriction, I'm sorry. Restriction from V of G. I'm sorry to bore you with this, but it's just the obvious equivalence relation. Get used to it. Just get used to it. It localizes at a point, and we localize this at this point. Okay. Okay. And that's that. And so if you have that, you have the embedding we talked about here, which I emphasize depends on a coordinate, z, in the formal power series. And now you can see why I want to call the variable in the formal power series big Z. Okay. Okay. Now, suppose we have an isomorphism here. So I'm talking to Kevin over in the Nordmental, and he's an algebraist, and he says, well, this thing's a stupid thing. I can write down a lot of isomorphisms to this thing. Right? Okay, so Kevin, I call this kappa for Kevin. So Kevin gives us you tell him at lunch if you see him that I call it an isomorphism Kevin. W. Now, these things we just talked about, what the devil they are. They're completely stupid things. I just talked about what it is. You just find something that works and you put it in and that's it, basta. I mean, that's something that really my grandson could do at age 6. I mean, really. You just find some formal power series, W equals that, and you put the stuff in and that's it. Right? That's it. Maybe it's not an isomorphism. You ought to watch out if it's an isomorphism. But if what you need to know is if you have Z appearing here as the lower order term, this will define an isomorphism. Check it. You have to invert it. Invert it means you have to invert it. You have to write a power series inverted. You have to write a power series inverted. That means instead of writing W in terms of Z, you write Z in terms of W. Because this is first order, this will be a finitary operation. You will do nothing. You understand there's no convergence. It's just recursively defining the coefficients. This you can teach a computer. Okay? You can invert it. So Kevin can invert it. Kevin converts this, so Kevin's saying, ha ha ha, this is trivial subject complex analysis, I can do that. And I say, Kevin, this guy here that you introduced may not preserve the notion of convergence. Will it? Is it clear? So is it clear? That Kevin preserves the notion of convergence. I don't think it is clear. I think it's false. Why? If it does, Z conversion is going to convert. P of Z equals W, that would have to be converged. But that would be the higher order terms would have to converge, right? And you can put here anything you want in formal power series, right? You can put here anything you want. Yes? You can put here anything you want. Yes.
But when we have this kind of isomorphism, does that then, I mean, we also consider a different radius of convergence.
I'm glad Nico is pointing this out. I didn't say, I said very carefully, and he's forcing me to be precise, preserves the notion of convergence. This means that if rho on one side is positive, then you take it over in the new series on the other side is positive. It will not be the same rho, obviously, because the coefficients will be all screwed up, right? It won't be the same rho, right? So it will take rho on one side to some other rho in some incredibly complicated way that I don't understand probably, but I wanted to preserve the notion of convergence. In other words, I think that the key thing is that this converges. So that means that P is a convergent series. So I tell the Kavon, it's not clear. In fact, it does. In fact, it will not in general. In fact, it will not. In general. So W equals P of Z should be convergent. Must define a convergent series. Obviously, right? That's necessary and it's also sufficient. Okay. So I go to the Nordmetall and discuss with Kayvon, which I like, and we have a big fight. And he says you can do anything you want, because he's an algebraist in this context. He's also a good analyst, but I won't tell you that. And so he says you can do anything kappa, and I say, well, no, you can't, because then it won't converge. And so what you have to have is that kappa has to preserve convergence, and that means that this series should be convergent. And now look what the heck that means. That means that Bob is this. This is the Z is the coordinate. W equals what do I call it? P of Z? Yeah, P of Z. I guess I call it P of Z. Is the function. Is a coordinate. And this is the induced mapping, maybe I call it K1 hat, and it's also obviously an isomorphism. Get it? That's the reason we introduced diagrams in mathematics. They're visually easy to understand. I have, Kayvon tells me in the Mensa that we have anything here. And I say, Kayvon, no you don't. We need to have P of Z is converging. It has positive radius of convergence. Rho of P of Z is positive. In general, it won't be. Okay, that's an isomorphism which preserves convergence. That means it lifts to an isomorphism of these things. What is these things? Here is Z is the linear coordinate in C. Here, W is the linear coordinate in C. This mapping, W equals P of Z. This is the point. Almost all of my life, I have been confused by classical mathematicians who talk about change of coordinates. And they write, you've seen it. They write, well, we have the S and T, and we have X and Y, and we have S equals S of X and Y. I don't know. And they're all sorts of complicated things, right? Again, you have Kayvon's formal mapping. It can be lifted if this is convergent, and it means that this power series is convergent into Z. That means that this thing really exists in the complex numbers. It's in the image space of this mapping. The way to think about it is, if you have the Z plane, and you have the W plane, Z and W are linear coordinates. You understand what I'm saying? They are the standard coordinates here. But the point is that they are connected by this map, W equals P of Z. And this mapping is only defined here. Right? Because it's only convergent in some small neighborhood. I don't know where the heck it's defined. You understand what I'm saying? Right? Kayvon doesn't care at all about what's defined here. Right? It's purely formal. It's anything. And then I say it has to preserve convergence. That says this function, if you want to call it that, has to have positive radius of convergence. That means this whole mapping has to be defined on some neighborhood of 0. The coordinate itself is the W plane, linear W coordinate. The coordinate here is a linear Z coordinate. The change of coordinates is from the linear Z coordinate to the linear W coordinate, but the change only exists on some small thing, because that's the radius of convergence where it exists. Okay? And now watch. I have exactly 5 minutes to prove the fundamental theorem of the subject at the beginning. Watch. Okay, here goes. Okay. So I start with Kayvon. Okay. I start with Kayvon. I take something, I'll probably screw up these things here, I don't know. Let's see, I take, I'm down here, I'm trying to do what Kayvon's doing. I'm trying to do this, what Kayvon's doing. Okay, so I start, well, I'll start downstairs, and I'll start with a power series that looks like Z to the order of this power series. Okay, you can imagine what that is. That's the first order term I factored out. Everybody can do that, right? Times the 1, and I'm going to really neglect the top coefficient all the time here. You can work it out yourself. Okay, I could call that A or B or something, but I just don't want to do it. Okay, 1 plus Q, and Q should be in there. You agree? If I start downstairs with something, I'm downstairs. So P is down here. And what I'm trying to do is define P of Z. Well, here it is, P of Z. Well, that's no good. And then I say, this is Z to the OP times 1 plus Q hat OP. I've solved the equation 1 plus Q, so something that's a unit plus something, the maximal ideal, equals 1 plus Q hat to the OP. Okay? Now, you pay your money, life is capitalistic. You pay your money and take your choice. How you do that. Okay. You can write down these things with power series, and you write down the recursion formula. You're trying to find Q hat. So this thing is called finding a root. Right? I found a root of something. I've given this thing over here, and I find this thing over here. Right? So you write down the formal power series of these things, write a recursion formula, which you can do for the coefficients in there, and you're done. Except you have to check, when you're having fun, that it preserves convergence. Okay? So this is an implicit question of this is given to you which converges. Solve this thing which is given to you which converges. You can solve it formally. Can you solve it convergently? You can do it by hand, or you can think about general principles. And if you want to think about general principles, you could think about the theory of Michael Arthur. He proves theorems of a general type of if you have implicit questions like this, if you can solve them formally, then you can solve them convergently. That's really interesting, right? A theory that works in some generality rather than having to do every time checking whether the darn thing converges or not. You can do it here. So this thing is equal, well, that's good. And now, I say, well, that's equal to Z to the 1 plus Q hat to the OP. Okay? Where everything in here is convergent. And I call this thing W. Right? Now I have to check that my principle is fulfilled. Caveman can do that if he wants, because it's formal. But it's clear that everything here is convergent, so that is convergent, so this defines an isomorphism. Okay? It says that by not defining the isomorphism that way, so in other words, the new coordinate is W, which is that, and the isomorphism is this. It says that if you employ this mapping, W equals P of Z, right? W equals P of Z. I organize it so that in this place, well, there's another P probably. I don't know, maybe it's almost, yeah, okay. In this place, this thing is just P to the N. So this is, this is not the same P. I mean, this is some given P. Let's call that P. Yeah. Okay. So here's W. So W equals P of Z. This is W equals P of Z. You get what I'm talking about?
What is O of P?
Hmm? Oh. Yeah. I think I said it, but didn't write it down. If you have any formal power series, it starts someplace.
Okay. Yeah.
Then I factor out that leading term. Formally, I have, obviously, this decomposition. But that's also obviously convergent because the radius of convergence doesn't change. Okay? So that's the order, and the rate, and O you should think is order of vanishing. Okay? So that's order of vanishing. Okay? So, what I've proved here, just from the point of view of this formal convergent point of view, which is exactly the point of view of Michael Arden. This is the son of Emil Arden, by the way. What we proved here, and this is concrete here, this is no big deal, is that by using roots and elementary stuff about convergence, you have a formal isomorphism which induces a convergent isomorphism, which means that this isomorphism, this mapping induces a convergent isomorphism of the local rings, which means that this is a bihomomorphic change of variables. Yeah, because I can invert it. If I can invert it down here, I can invert it here. Okay? So it means after a bihomomorphic change of variables, every holomorphic function f, which I regard in the local ring, is of the form. So we're saying with f of 0 equals 0 is of the form f of w equals w squared, or something like that. W, okay, whatever. It says the complex analysis in one variable, the local theory, is a triviality. Right? You just employ K1, and K1 says, well, that's trivial. Right? And I say, no, K1, it's not quite trivial, you have to watch out for conversions, but he says, okay, that's also trivial, he's right. The minute you do that, you lift to the local rings, and you get an isomorphism of the local rings, which says that this is a bihomomorphic change of variables, which says after that change of variables, every function, depending on the order of vanishing. You see, the only invariant here, and I'm glad Nico asked her, what is the only invariant of the function is the order of vanish. Yeah. Only invariant. Is the order of vanish. That's it. That's, by the way, from my point of view, an amazing theorem. But you saw the proof. It's very easy, right? There's nothing. I did nothing. Okay. And this is not true in higher dimensions. Not even close to being true. Okay. And that is one reason that the local theory in complex analysis in higher dimensions is really non-trivial, and the local theory here is trivial. You understand? This is the local theory, so to speak. You're looking, Nico, you're looking mystified.
No, I was just thinking about something you wrote earlier. Because you said with the change of variable that W is P of Z, being Z plus some higher order term.
That's right.
But here we basically say that if our change of variable is F,
where maybe I mixed up.
so the bihomomorphic change of variable.
No. Oh, yeah, I'm glad you asked. Yeah, please go on. And then, yeah.
So does it mean, no, so if F is the function which does the change of variable, then we don't get a combination of.
No, I confused with my lousy notation. Okay, let's go through the logic because it's very nice logic. Okay, F. Let me turn it around now. I go to Neumetall and ask K1, I'd like to introduce isomorphism at this level and change variables somehow to simplify a function. That's somehow where you're starting with, and you're starting with, so to speak, the end result. And then Kayvon says, I don't want to do this because I'm an algebraist. I want to do it at the formal power series level. And then he does it at the formal power series level, and it's all wrong because he didn't get convergence, but I tell him, and he says, okay, I'll just force convergence like this, and then I know it. So we produce it here, okay? That means we lift the map here, and the map here is given by the map down here. So Kayvon hat of let's say, no, not hat, of a formal power series here, Kayvon hat of W is, no, Kayvon hat of, I don't know, Q is bad, equals Q of P of Z. Okay? Any Q. And now Kayvon hat of F is equal to F of P of Z. Okay?
I think I have to think about it.
Okay, but don't, no, I think what's going to help clear this up a little bit, I think this is a beautiful thing, so I want to emphasize it, is I started with something, it's a question, because Nico is absolutely right. You should think like, think logically. I start with Z to some power times 1 plus Q of Z. I call that F of Z.
And where is P?
Hmm?
P is just.
Oh, no, I'm sorry.
We don't have.
Oh, F. That was Freudian, because I'm going to go to P, I think. Okay. And now I come downstairs to Kayvon, and I have Z in the formal power series ring, order, I'll call it F, 1 plus Q of Z downstairs. Right. And I call that equal, and now I take a root, I'm lucky. So this is Z times 1 plus Q hat, downstairs, Kayvon. Okay. Now I call this W to, yeah. Okay. And now this transformation was W equals P of Z downstairs.
Okay.
And now I define the transformation upstairs by, I've written this someplace, W equals P of Z. And then P of F, oh, okay, it just follows it, I mean.
Yeah.
Okay.
Just substitute.
So intentionally I went back to this proof to tell you how I'm thinking about this stuff. I think it's really a beautiful thing to see that this subject is only formal. It's almost just algorithmic. Yeah. And it's I think one of the reasons why curves means one-dimensional geometry, play such a big role in arithmetic, in number theory. See, you try to do number theory on higher dimensional stuff, it's difficult, much more difficult. Anyway, thanks for your patience today. I think I explained what I wanted to explain. Have a nice week. I think we need to catch up the lectures I'm going to miss. And I think you agree it's okay to have noontime on Tuesday. We'll have a little gap and go on. And I will post the lectures, what they are, on the website, okay?
So when are we gonna make up, or no, when are we gonna miss classes? Or
Yeah,
next week?
will it help you now if I tell you when we're gonna miss? Maybe.
No, it sounded like we're gonna miss class next week already. So.
No, next week not, but then start missing for 3 weeks and then start up again.
Oh, I see.
Okay. It used to be that 2 of those lectures were reading days,
Mm-hmm.
but they changed the academic calendar. There's no such thing as a reading day anymore. So I need to make up 6 lectures, but I will lecture like this, just telling you all sorts of things in mathematics that might be useful for you. And you should ask stupid questions, and like he asked a stupid question. No, it's a good, he asked what, in adult language, he asked why are we using this topology on the complex plane? Why not some other topology? That's in some sense what you asked. And that's a good question. Yeah. So ask your stupid questions. They'll be good. Thank you for your patience.